Anybody recognize this question? I think it was in the notes from the booklet, at least. All right. So a radioactive isotope of hydrogen that is made to used to make paints that glow in the dark has a half-life. Right. The half-life of tritium is 12.35 years. Okay. So we know that at time 0, at the very beginning, there's 100% of it in the paint. Make a table of the relative luminescence, the amount of light, I guess, it glows over time for at least 3 half-lives. Okay, so we're going to do that. So time is in years, and percentage, right? Percentage remaining, basically, you can call this, or doesn't really matter. Just whatever you come up with. So at time 0, you have 100%. So here's where it comes down, right? So what is the half-life? Well, the half-life is 12.35 years. Okay, so you add 12.35 to 0, and then this would be divided by 2, right? So this would be 50. So you're down to half of what you started after 12.35 years. Do that one more time. Okay, we add 12.35, that would be 24.7. And so half of 50 is 25%. It says to do this for 3 half-lives, so technically we'll add another 12.35, so that's 37.05, and so half of the previous one would be 12.5%, but it never really gets to 0, okay, based on this model, because you can keep dividing a number in half indefinitely to infinity. So I would give you a mark for this. Determine the equation. So we're going to go stat, calc, exponential regression. And when you do that, you get 100, which is what you start with, 0.9454 to the x. Okay, so that's 3 make a graph showing 50 years worth of time. So if you use, this would be 3. So this would be time in years. This is percentage remaining on the y-axis. And so we need to start with 100, right? Or at least fit that in. So 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. So I'm going to start at 100. And I want to include 50 years. So I'm going to go 10, 20, 30, 40, 50, right? I'm going to label every other one, but it's understood that your scale is 10. All right, so it's important, it'd probably be good to find that point. So second trace 1, x equal to 50. Let's have that as a reference. Y would be, no, not, do I say 50? Yeah, I do say 50. What's my point there? 6.04? Okay. 6.04% remaining. Very close to the x-axis, right? So we start here. We are going to end up very close, but not on it. Okay. And then you find one more in between. I think I found 25, and that was 24.58. So 25 is right about here. So that's 10, 20, 30, but I'm in between. So that's to help me have a bit of a reference, and then I just go from there, curving, but not touching. It's okay to keep going because it just says show at least 50 years. It doesn't say that it stops decaying or anything like that. So in this case, arrowhead is okay. That is an arrowhead, believe it or not. Okay, so we have the equation. You've got labels, percentage is your unit, and you've got everything else you need on here. So that would be, I didn't give you a number here. I'm going to go with 3 marks again. So 1 for labels, 1 for scale, and 1 for the correct shape of the graph. Okay. 4, what will be the relative luminescence after 40 years? So they're saying, hey, if time is 40, what's y, right? Because we know all along time is x, the percentage remaining is y. So we're going to go second, trace 1, x is equal to 40, y is equal to, hold on, 10.59%. So this would be a mark as well. So 3 for graph, 1 for question 4. And then question 5, how long will it take until the relative luminescence decreases to only 1%? So they're saying how long if y is 1. It's basically what they're asking. So y2 is equal to 1, second trace 5. And of course you need to make sure your window sees that intersection, right? So you might have to increase your x max to make this possible. And you get 82.05 years for that to happen. Also 1 mark for that. So we are at 1, 2, and 3. That'd be 5, 6, 7 so far for this page. What would be the domain and range here? I'm not going to give you marks for this, but what would you say is the domain? Domain, we start at time 0. It's inclusive, right? And according to this, we don't know when it stops. My range, this one is tricky. My range, does it ever touch 0? It gets awfully close, but it never actually touches. So you would say 0 round bracket all the way to the highest it ever gets to, the luminescence, right? The y-axis is 100. So I would write this down for sure here in this case. Not included, right? Very important to have round brackets. 0 is not included. All right, that's just a freebie. Backside. What's the doubling time here? Well, you have 2,500 to start. So y2 is going to be 2 times 2,500. It's going to be 5,000. I'm wondering how long will it take to get from here to here? And then you go second trace 5. I don't have this entered yet, so bear with me. I'm going to turn off plot 1. I don't know if I, there, 1.015, close it to the power of x. For my window, I'm going to let y2 equal 5,000 already. For my window, I better include way more than 110, right? So I'm going to go 10,000 or something like that because I know I'm increasing. Right? I know I'm increasing because b is bigger than 1. So let's try that. Works pretty good. There we go. It shows. And so x is going to be 46.56 years. 1 mark for that. 1 mark for that. B, this was A, right? So B, what does this mean? That the deer population doubles every 46.56 years. That's what that means. I couldn't have asked you for the half-life because this is an increasing function, right? So there could be a deer population. There could be a model that shows a decreasing deer population because maybe too much hunting, road kills, what have you, right? So it doesn't always have to go up. So 2 marks at the back here, right? All together. So you've got 2 and 7. That's 9 total. Just make sure your name and last name is on there so I know who you are.